Hi, Algebra 2. Wanted to take a look at the notes for section 7.1 on exponential growth and decay. And go ahead and take a minute and write this down, the definition of exponential function. Remember, you can always pause the video for a moment to write down what you need to write down. So a function with a variable as an exponent is an exponential function. Exponential function is going to look like f of x equals b to the x. The base b is a constant, and the exponent is your independent variable. So that's where you're going to substitute in your 0, 1, 2, 3, 4 if you were making a table of values. B has to be positive, and B cannot be equal to 1. And why is that? Well, if B is 1, the value of the function is always 1. No matter how many times you multiply 1 by itself, it's going to be 1. The parent function, f of x, equals 2 to the x. So what does that look like? So this is the graph of f of x equals 2 to the x. And I'd like you to take a moment and just kind of note some of the things that you see here and maybe write them down. So some of the things that maybe you wrote down, you notice the y-intercept. The y-intercept of the parent function is 1. When x is 0, y is 1. And that makes sense. 2 to the x, 2 to the 0 power, anything to the 0 is 1. When x is 1, y is 2. 2 to the first power is 2. When x is 2, y is 4. 2 squared is 4. And when x is 3, 2 to the third power is 8. And when we follow up to the curve, we find there you have the 0.38. What's going on over here on the negative side for x's, though? Well, remember when you have a negative exponent, that creates an inverse. So when x is negative 1, 2 to the negative 1 is 1 over 2, right? 1/2. Negative 2 is my x. 2 to the negative 2 power is 1 over 2 squared, or 1 over 4. And so these values are going to get increasingly small. When you have negative 10, 2 to the negative 10 is 1 over 1024. It looks like it's 0, right? It looks like it's on the x-axis. It approaches the x-axis, but never touches it. So I'd like to talk a little bit about exponential growth and exponential decay that can be modeled with this type of function. So a function of the form f of x equals a times b to the x, where a is positive and b is greater than 1. Okay? So if this is the case, the value of this function is going to increase as x increases. And if you think about that, that makes sense. Even if I had something just slightly greater than 1, 1.01, and 1.01 times 1.01, when you multiply that out, you're going to get something like 1.002 or something kind of like that. It's not a lot greater than 1, but it is greater than 1. If you wanted to, you could go to your calculator and get that number. .0201 if you want to get technical about it. Well, what happens when b is less than 1? Now remember, b has to be positive, but it's possible it could be less than 1, between 0 and 1. So if that's the case, when you have a function f of x equals a times b to the x, and b is less than 1, the value of that function is going to decrease as x increases. You're like, well, how can that be? Well, let's look at a simple example. If I have 1/2 times 1/2, that's 1/2 squared, that equals 1/4. What if I had 1/2 times 1/2 times 1/2? That's 1/2 to the third power, and that's 1 over 8. Okay? So you can see that as I repeatedly multiply 1/2 times itself, it keeps getting smaller and smaller and smaller. Half of a half of a half of a half. If we're eating pizza, right? You take half, I'll take half. Now somebody else comes along and they're going to get half of my half. Somebody comes along and gets half of their half. Well, they're getting a slice, right? You keep taking half of a half of a half of a half, it's going to keep getting smaller. So let's look at a quick example. Does the function f of x equal 1.5x model growth or decay? And how do we know? Well, what are we looking for? Well, we're taking a look at, is the b value between 0 and 1? And the b value is 1.5, which is greater than 1. Okay, so I know that has going to represent growth. All right, so the b value greater than 1. So let's go ahead and try another one. All right, so a new vehicle loses a certain percentage of its value every year. Which graph could represent the value of the vehicle over time? So we look at these 4 options, and we see the first one is a parabola, right? And as x gets greater, the number of years increasing, this value is going up. So that doesn't seem like this function is losing value. It looks like it's gaining value. This graph, kind of unusual. It increases rapidly, but here the value is negative. Could I have a value of a car that's negative? That doesn't make much sense. And then it flattens out over time, keeping whatever value it has. This one, this shows decline, and this is a straight line, so this is linear. So this would say that it loses the same value every year. Okay. And then this one is your exponential decay graph. Okay. So let's think about that for a minute. Which one of these appropriately models vehicle losing a certain percentage of its value over time? So if I had a vehicle that was $10,000 and it loses 10% of its value, let's say, 10% of 10,000 is 1,000. So if I subtract that, 9,000. Now the next year it loses another 10%, which 10% of 9,000 is 900. So now that car is worth 8,100 after a second year. It loses another 10% of its value. 10% of 8,100 is 810. And if I subtract that, I get 7,290. Another 10% would be 729, and so forth. So you can see that each of these figures represent 10% of the value, but it's not a constant loss in terms of actual dollars, 1,900, 810, 729. So that could not represent a linear relationship. So it's got to be B. All right, so go ahead and pause the video and write this formula down. The model of growth or decay by a constant percent increase, which is what we just talked about. A of t equals A times 1 plus or minus r raised to t. And so you can see here that A is your final amount, capital A of t. Little a is your initial amount. Your growth or decay factor happens here because we're either adding or subtracting the percentage increase or decrease from 1, and then the number of time periods here. So let's take a look at what that would look like in our car example. So if the car's initial value was $10,000, that would be my initial. It's losing 10% per year. So 1 minus, and then this is critical. If I go 1 minus 10, I'm going to get negative 9. That's not going to make any sense here. That value can't be negative, right? So I have to make sure that my percentage, I turn into a decimal, which means divide by 100, and then to the value. So the value of this car could be represented by this function. And the 0.9 multiplied repeatedly, that's what was happening here. So let's test this out. A couple buys a house for $200,000. The value of the house appreciates at 7% per year. Which equation models this situation? So we want it to look like A of t equals the initial value times the growth or decay factor raised to the number of years. So what is our initial value? $200,000. So we know that this value, little a, has to be 200,000. And in each one of my options, I have y equals 200,000 times something. So now I'm going to start looking at this value here, 1 plus or minus. So the house is appreciating, which means increasing. So it's going to be 1 plus some value. Okay? 1 plus 7%, which is 1.07. All right, one last try here. So this is the same information. A of t equals 200,000 times 1.07 to the t. And you want to read this question carefully. It says, how much is the value of the house increased after 4 years? So we're not being asked, what is the new value of the house? It's saying, how much did it change? It started at 200,000. What's it going to end up with after 4 years? So let's look at how we could work that one out. So A of 4 equals 200,000 times 1.07 to the fourth. Okay? So we go to our calculator. 1.07 raised to the fourth power. 1.31 something, 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 something times 200,000. 262,159.20. Okay, so is this our answer? No, because we still need to subtract off our 200,000. How much did it change by? 62,159.20. All right, so good work. And if you still have questions on this, feel free to go ahead and ask those next time we meet together in class.